Okay. So first of all, we have what? We have GCD of A and B is equal to 1, right? From 6, this implies what? This implies GCD of AC and BC is equal to C. Does that make sense? This is by 6. Is that okay? Because A divides AC, because A divides BC, so A divides GCD of AC and BC. Does that make sense? So this is by the linear combination, so by our earlier theorem, because this is a linear combination of AC and BC. And what is it? This is C. So A divides C. Is that okay? So we don't need prime factorization theorem to get this result. But then it will be super difficult. Yeah, but still, I hope you find it interesting. Now finally, I have a star that I think this is interesting and also important. So we want to show that GCD of A and B will be equal to GCD of B and A mod B. So what is A mod B? A mod B is so by unique factorization theorem, let's say when A is divided by B, we get A is equal to QB plus R for some R between 0 and B minus 1. Then we call R, we define this R to be equal to A modulo B. Is that okay? The remainder of A when it is divided by B. Okay, so A mod B. So we want to show that AB is equal to B A mod B. So first of all, A mod B itself is a linear, this number, A mod B is equal to what? A mod B R is equal to this one, is equal to A minus QB. Is that okay? So this number itself is a linear combination of A and B, right? B is a linear combination of A and B, of course. 0A plus 1B, right? And GCD is a linear combination of these two things. So GCD will be a linear combination of A and B. Is that okay? GCD of these two is a linear combination of A and B, so GCD of AB divides this part. Okay? Okay. You can use A and B to create B. You can use A and B to create A mod B. Then in that case, GCD of AB will divide this part. Is that okay? So we just need to show the reverse. Okay, the other side. Okay, B is equal to B, right? But you can use B and A mod B to create A. How do you create? This one. How do you create A? Yeah, this one. You just have Q copies of B, and then one copy of this A mod B, you can get A. Is that okay? So this is a linear combination of B and the remainder. A is a linear combination of B and this remainder. So this overall thing is a linear combination of these two terms, so it is divisible by this part. Is that okay? So the right-hand side divides the left-hand side, the left-hand side divides the right-hand side, so they have to be equal. So this is the proof. Okay? Okay, good. And why is it important? So this gives us the Euclidean algorithm. So let's have two very large numbers. So for instance, 1, 3, 5, 7, 1, okay. And then 2, 9, 4, okay. And then let us try to find out what is the largest common factor. Oh, greatest common divisor. Okay, the greatest common divisor of them. Okay, so we don't know. But we know that the greatest common divisor of these two is equal to the greatest common divisor of 294. So this is a smaller number, right? And then, and we don't need this large number. We just try to divide this number by 294 and then get the remainder. Okay, yeah, 294. Let's multiply by 3 times or 4 times. Yeah, I guess we can make it 4 times. So 4 times of this number, what do we get? 4 of, 1184, something like this, right? 4 times of, 1186. Is it? No, 1176. Yeah, that's 294. If you multiply it by 4, so what do we get? So this is 16, 7, something like this, 1176. Am I correct? 1176. So 13, no, oh, too large. So let's use the long division. Don't be lazy. Let's use 13571. If we try to divide it by 294, what will happen? So we should get a 4 here. 5 is too large. So 4 is 1176. Am I correct? So we get a 1, we get a 1, we get an 8, we get 1. Is that okay? Does that make sense? Looks like we can get a 6 here. Yeah, because it is roughly 300. Yeah, 6. So 64 is equal to 4. You have a 2. 69 is equal to 54, right? So 56. 62 is equal to 12, so we get 1764. Is that okay? 1811, 1764. So if you deduct it, so you get a 7 here, and then you get a what? You get a 4 here, and that's it. Am I correct? So 47. Oh, super nice. 47? Is it? Yeah, okay. So let's try 47. Okay, 47. So now, instead of having 47 and 294, so we can keep one part and then replace the other parts by the remainder when it is divided by this one. So 294 when it is divided by 47. Yeah. So let's have 7 is too large, right? 6, 6, okay. 4, 2, 8. Okay, we get an 8 here. Is that okay? No, 12. Yeah, too bad. 12. 12. So it is a 12. And then, yeah, by our heart, yeah, we know that 47 and 12 is equal to 1. Let's change the number a little bit, okay? So for instance, let's make it 1 larger. Then it is going to be 13572. So we get 48 here, and we get 48 here. Is that okay? Okay. So we get 48, 12 here. So we can actually continue to do this. So we keep the smaller part, and then divide the other by this one, and get the remainder. So we get 0. Okay. Now, when we get a 0, then we immediately know that the non-zero part will be the greatest common divisor of these two numbers. So it is going to be 12. Is that okay? So it is the so-called Euclidean algorithm. And why it is correct? It's based on number 9. So it is called the Euclidean algorithm. Why is it good? Why is it good? How many steps do we need? Can we analyze? So we have two numbers. Let's say this is called A, and let's say this is called B. Is that okay? So first of all, will this algorithm stop? The first question is, so we have an algorithm, if it can go infinite, it can go into infinite loop, then it's not a good algorithm, right? So we start with two numbers, and then what we do, we make the larger part smaller, right? By doing the modulo operation, and we get another two numbers. We get the larger part of these two smaller. Is that okay? And then so on and so forth. Until when? Until one of the two numbers becomes 0. Is that okay? And then we stop. Okay, so first of all, will this algorithm stop? Yes, it will stop. Reason, at least one part is going to decrease. So one part may be not changing. So here, this part is not changing, but the other part is going to decrease. So it is like you're running 2 stairs. Either this go down or this go down. So we go down one of them at each time. So one of them must hit 0 eventually. You cannot go infinite steps. Okay? So it will stop. And then how much time does it take? How many steps does it take? How many steps? So we claim what? So one number will get decreased, right? Right? So here A will get decreased or B will get decreased here. Is that okay? We want to argue that the number that is going to decrease is going to decrease at least by, is going to at least decrease into half of it. So we have an A here, we have a B here. Okay. So we're going to say that this number cannot be greater than A over 2. Reason, simple. If B is less than A over 2, the remainder cannot be A over 2, right? Right? On the other hand, if B is greater than A over 2, then this remainder cannot be greater than the difference between A and B. You need to at least minus 1 of B, right? And B is at least A over 2 already. So it goes down by a factor of 2. Is that okay? So each time A goes down by half, into half, B goes down into half, and so on and so forth. So the total number of steps is going to be bounded by order of log A plus log B. Is that okay? You only have log A steps, log B steps to go down. Okay, usually we will just write it down as log of the max of AB. This will be sufficient, okay, because we are taking order. And so this is a polynomial time algorithm. Okay. In contrast, if we try to get the greatest common divisor by what? By trying, if 1 can divide both of them, 2 can be dividing both of them, 3 can be dividing both of them, until whether B can divide both of them, then it takes order B time, and it is an exponential time operation. Okay. Okay. Is that okay? And it turns out that what is the longest sequence that we can create with the smallest sum of the two numbers? It turns out that if we use Fibonacci numbers, then you will need many steps, and this is the case. So Fibonacci number. So let's have 2 consecutive Fibonacci numbers. So let's say we have 89 and 55. Is that okay? Is that okay? So we have 89, 55. So, okay. So we keep 55, but then we will have 34 here. Is that okay? And then we will keep 34, and then we keep 21. And then we keep 21, and then we have 13. And then we have 13, we have 8, and then 8, 5, 5, 3, 3, 2, 2, 1, 1, 2, 1, 2, 1, 2, 1, right? 2, 1, 1, 0. Is that okay? So that's it. So this is going to be the longest path. Okay? So yeah, I hope you like this. So today we don't have time for this fundamental theorem of arithmetic. Maybe we can talk about this on Thursday after the tutorial if we have time, or after the exam. Okay? Let me ask you one. So this is a game, okay? A game between 2 persons. So this is called takeaway game. Okay. So we start with 2 numbers. let's say these two numbers, let's say 80 and then 24, okay, 80 and 24. So one number has to be larger than the other number, okay. So what? So when you have one large number, one smaller number, we need to take some multiple of the smaller number from the large number. So we can make it into what? If we take one part, so this will now become 56, 24. Is it okay? So this is one possible scenario. Or we can take 24 two times. So in that case, we will have, so this could be 32. Is it okay? 32 and 24. This is the case where we are taking this two times. Or we can take it three times. Is that okay? And then leave it for the other player to play. So this takes turns. So there are two players. Okay. When we have two numbers there, we need to take at least one copy, or at most how many copies? So of the smaller number from the large part. So this is one of the case. So if the first player takes one copy like this, then the second player can choose from this copy or this copy. If the first player takes two copies like this, then the second player has to choose this one. If the first player takes three copies of this one, then the game becomes 8 and 24. Okay. And then the second player can make it into 8, 16, 8, 0. 8, 8 or 8, 0. Okay. Now, who is the winner? The winner is the one who can take it so that in the end, one part becomes 0. Because when one part becomes 0, then the game has to end. Right? You have one part 0, then you can, whatever the smaller part you take, then you can do nothing. Okay? And then for this game, is there a very quick way to determine who is the winner? Okay, so you can solve this game to find out who is winning easily by using dynamic programming. Perhaps, okay, perhaps. But then, is there an even faster method to find out, let's say this game, who is going to win? Okay, so this is, I will tell you more about this later, okay, if we have a chance. Okay, so let's end the class today. Thank you.